So for our project, we were working on designing a wireless bidirectional charging system for electric vehicle. In particular, my portion of it was going to be dealing with the power electronics that would be on the car side of the system. Um, so as part of that, that includes being able to both rectify a AC signal that is being transmitted across an air gap via some copper coils, and then as well as being able to invert a DC voltage coming from a battery so that it can then be transmitted across those copper coils. Blake, on the other hand, was responsible for dealing with the power electronics on the grid side of the system. So, due to the fact that most of our electronics were going to be very, very similar, we came to the conclusion that it would be easier for us to work together and kind of split up how the power electronics were going to work in order for us to not be overlapping and doing the same work. So the portion that I took on was the rectification. So I have some simulation models of how we're going to be doing the rectification for both the car side and the grid side. And Blake will have some details on how we're going to be doing the inverting on both sides as well. So to start out with, the original plan was to use these switching rectifier. Basically using these NMOS or possibly some IGBTs in order to rectify an AC power signal. We ran into a couple problems with that, namely being that the power MOSFETs are not easy to simulate in LT-Spice or in any P-Spice simulator for that matter. We spoke with a couple professors about the issues that we were having and determined that really they're hard to use in simulation, and so we decided to substitute instead a voltage controlled switch to be able to model the same thing that these switches would be doing. So here we have what our original schematic was planned on looking like. We have our switches here. Over on the right side are our control signals. So we're sending a square wave with a certain duty cycle to control these switches at each one of these, reference to the VGS of each transistor here. So, and then we also have these voltage controlled switches so that we can open up, in this case, it would be switches 4 and 2 when we are in the positive half of the sine wave, and then switches 1 and 3 when we were in the negative half of the sine wave, coming from either the grid or from the wireless transmission coils. The idea being that then switching them in that manner with a capacitor, a smoothing capacitor here on the output, we would be able to have a rectified DC signal. Again, these power MOSFETs were not operating in the way that we would like to have seen. We were getting some weird reverse currents going through them, and they were just not working in an ideal manner that was going to work for us. So we decided to replace those with voltage-controlled switches, which we can see here in this model here. So here we replace them with voltage-controlled switches. We have kind of our same thing here. We've got our smoothing capacitor here. We've got our 4 switches. Since we didn't have to reference a VGS on these switches, we only needed 2 controls, one to control and turn on the duty cycle during the positive half of the sine wave, one to turn on the duty cycle during the negative half of the sine wave. So again, this one, we still ended up having some problems here. These diodes here were meant to kind of solve those problems. We were still getting some reverse current going through these switches in directions that it shouldn't be when they were turned on. So the diodes helped solve that, as well as this inductor was there to help solve that as well by trying to keep the voltage in phase with the current, so we didn't have any negative currents while our voltage was positive, which could have been one of the reasons that we were getting negative current there. But that still didn't solve the issue entirely. So we added these diodes to try to help. Again, the problem that we ran into with this simulation is that basically we were getting a really big voltage division between this initial inductor and then the output. So we weren't able to transmit a reasonable amount of voltage here from AC to DC. We'd end up with really, really low voltages, even though we had a high duty cycle. We were able to get it to work to where we could control the voltage with our duty cycle. But that wasn't enough to boost our voltage to what we need it to be in order to have a functioning circuit. So that being the case, we decided to go with a diode rectifier. So that being the case, here's what a diode rectifier for what we're going to have on the grid side. In order for this to operate, in order for us to get our bidirectional functionality with a grid or with a diode rectifier, we're going to have to be able to have a manual switch connecting the input of the grid to both this rectifier, and then these two wires right here would also be connected to the switch, so that the grid could also be connected to the inverter as needed for when we were discharging the battery and putting power back onto the grid. So with that being said, we went with the diode rectifier and the manual switch. The end goal, of course, is to be able to do this all in one circuit, to be able to go back to something like this, or even back to our power MOSFET circuit. That being so that then we don't have to deal with two different circuits and a manual switch to be able to switch between the charging the battery mode and discharging the battery. So this was our ended up with what we had for our rectifier on the grid side of the power electronics system. So here we do have our 60 hertz sinusoid representing the grid. Here we have a load that was just chosen arbitrarily to basically sink 1.5 kilowatts, because that's the power that we are looking to transfer. We were able to simulate that. As we can see here with the simulations, we have our input currents and voltages. Our input current, our RMS value is 17.38 amps, so we're below our 20 amp threshold, so we don't have to worry about tripping a standard 20 amp breaker. And we have reasonable currents and voltages there on the input. On the output, we're able to end up with an average voltage of 135 volts. We're sitting at about a 10% ripple, which for our purposes here, that's adequate. As well as then we have a reasonable current level there as well that's going to be flowing out of the DC bus. Then we can see here we actually end up with a pretty reasonable efficiency. We have our input power, which ended up about 1.6 kilowatts for that particular resistor, and here we're at 1.67. So we can see that we actually have a pretty good efficiency here. Actually, it looks like we're getting more power out than what we're putting in. That's probably just because of the way that the LT Spice is calculating those powers here and calculating the average powers, as it only calculates for this particular time window. Towards if we took the whole time window, we would see what the actual efficiency is, and we would see that it's probably somewhere in the 90% range. So that's on the grid side. That's the grid connected grid side rectifier. So we're also going to have another rectifier here, which is basically going to be doing the same thing on both sides. So on the grid side, this rectifier will be connected to the coils, and when we want to be discharging the battery, it'll rectify our 20 kilohertz sine wave coming from the coils to our inverter, which is then going to the grid. And this is the exact same circuit that we're also going to be using on the car side for when we're going to be rectifying the voltage from the coils this time, still from the coils, but on the car side, and we're sending that voltage and that power to the battery. Both circuits are identical. There's not really a whole lot of variation between the two. So we can have our simulation results for this case. As you can see in this one, we have our 20 kilohertz sine wave coming from the coils. We have our load resistor to transfer about 1.5 kilowatts of power, smoothing capacitor here, and our inductor, which is there to limit the current going through the system so that we aren't drawing too much. So for our simulation results, again, we've got reasonable currents, reasonable voltages coming through here. We have an RMS current on the input of about 18 amps, so that's definitely within the range that we need it to be. Our output voltage, again, we're sitting right around a 10% voltage ripple here, pretty close to that. And we've got an average voltage of around 160 volts. So getting a little bit better voltage out of this one. That's partially due to the fact that we can use some smaller components, a smaller inductor and a smaller capacitor in order to achieve the minimum voltage ripple that we want, as well as the a reasonable current as well. And same thing here, got about 1.5 kilowatts of power coming in on average. Pretty close, 1.44 kilowatts power, and we've got 1.51. So same kind of issue here. We're seeing more coming out than going in, but again, that's just due to the way that LC Spice is calculating those averages. So again, I would expect that this is going to be somewhere around a 90% range, somewhere in the 90% efficiency. So with that being said, now that we've gone over kind of all the rectification, we also have developed our specs. So here's going to be what our grid side spec is going to look like. So over here we have the grid, 170 volts peak with at 60 hertz. Here are the manual switches that I spoke of, so that we can switch between whether we're charging or discharging the battery using these manual switches. So when they're in this position, we are discharging the battery. And then when they are in the up position, in that case, we were going to then be charging the battery. So when we're charging the battery, we're coming up through these switches. We come through our diode rectifier. We have our current limiting inductor, our smoothing capacitor, and then we hit our inverter, excuse me, so we can invert that at our transmission frequency of 20 kilohertz. And then we have an output filter there, so we can get our a nice sine wave out, and then we can go over to our coils here, which is represented by this 170 volt peak 20 kilohertz sine wave. When the switches are in the down position, then we're going to be having power coming from those coils, and it's going to go through this rectifier. Same layout. We have current limiting inductor, smoothing capacitor. We have our inverter with the filter, and then power is going back onto the grid. So then we also, coming down here, we've got all of our maximum and average values that are necessary for our component selection. So we have our charging mode, our grid side charging mode values here. This is our coiled side inverter. These are giving us all of our maximum and average values for that device. And then we have our grid side diode rectifier with similar values there. That again, we're using component selection. We also had to take this and we went and looked at the discharging mode as well, so that we can see what those values are, so we can kind of figure out a worst case scenario to pick the components that are adequate to completing this task. And finally, in this spec, we've got our selected components. Here we have our IGBTs. We have 8 of them, 4 in each inverter. We have 8 diodes, 4 in each rectifier. All the same. We were able to find ones that worked for all of our conditions there. Then we have our current limiting inductors. This O1 is a little bit problematic that we're going to look into. A 2.5 millihenry inductor that can handle the current we're looking at is fairly expensive, so we'll be looking at other ways of maybe looking to limit the current in another manner. As well as this 3 millifarad capacitor is fairly large as well. Other than that, it's all pretty straightforward. We have our smoothing capacitors and our filter capacitors, and then our resistors that are also used in the filters. And then this will be the gate driver we're using, which is going to be used to control the gates on the IGBTs. It does accept a digital input, so we'll be able to control that with a digital signal to be able to get the control that we need to get the gates, to get the IGBTs to switch how they are needed. And then this is a switch we found that for a manual switch that'll work in between the diode rectifier and the inverters and either the grid or the coils, so that we can control whether we're connected to the inverter circuit or to the rectifier circuit. We have a very similar thing here. Here's our car side. This 170 volts is going to be our battery. What we're simulating as our battery. We have our 170 volts peak 20 kilohertz sine wave on this side, representing the coils. Again, we have our manual switches to switch between the rectification and the inversion. Up top, we have our rectifier to rectify our voltage to charge our battery, and on the bottom, we have our inverter in order to discharge the battery and send power back to the grid. Again, here are all of our max and average values that we found and that were used in component selection. And here are our selected components. We have the ones used in the diode rectifier and the ones used in the inverter, which are also going to be the same as the grid side for the most part. The inductor and capacitor values will be different, and again, these inductors and capacitors are smaller, so they're not problematic at all. We'll be using the same gate driver with the digital input and the same manual switch that is capable of handling all the current and voltage that we are expecting within the system. So thank you.